Today's topic is going to be on how to solve derivative and concavity tests, inflection points, and using second derivative tests as well. So this is just going to be a conceptual video and go over the ideas of what these tests are. So first off, we're going to start off with an increasing, decreasing function test. So increasing, increase, decreasing. So you have a derivative f of x, and it's either greater than or less than 0 on some interval, then the function f of x is either increasing or decreasing on that interval. Alright, so that's going to bring us to the first derivative test. Sorry about the writing there, I'm just trying to be quick. Alright, so if you have a continuous function f of x, and there is a local minimum or maximum, we'll say max, min. I said, so if you have a critical point C, and f of x does not exist at x equal to c, then therefore f of x will have a local minimum or no local maximum. So no min-max, no local min-max anyway. So next idea is that at a point where f prime is going to change from either positive to negative or negative to positive at C, then that means there's either a local minimum or maximum at C. Sorry, I kind of said that backwards. It's actually a maximum or a min in terms of the way that I said that. So then our next test is going to be concavity test. So we're going to go over concavity and what that is, and the concavity test. Okay, so if a function f of x is above or below the tangent of that function over some closed interval, then it's called a concave upward or concave downward. In 1 second, I'm going to write this out. And I'm going to explain exactly what this means here in a second. Okay, so if you have a graph, you have some function f of x on an x-axis, you have some interval, and if you have, it looks like this. So remember, at the very top your tangent's flat, and I'll make two graphs here. I'll show you what concave up and concave down looks like. This is just a very simple example. Remember, you have a flat tangent there. So, like we said, if f of x is above or below the tangent, so what's going to happen is that here, when you write your tangents along each part of the line, and remember, you're going to have straight lines that will become tangents to it at every single point. Now here, the function itself, f of x, is on the bottom. So due to our definition from above, if it's below, it's concave downward. Therefore, this is going to be concave downward. And then, like as so, if you draw your tangent lines all up the sides here, you'll see that our function is above. Therefore, this is concave upward. And that's the idea of what concave or concavity is. Another way to test this is to take the second derivative and say if f double prime of x is greater than or less than 0 over this closed interval, then f of x is concave upward if it's greater than 0, or downward if it's less than 0. The next point is going to be about inflection points. So, the idea of what an inflection point is when you have a function that has both parts that are concave up and concave down. So just give me a sec here, I'll draw this out. And so you have a part that's concave down, concave up. So the region where it switches from becoming concave down to right here, right somewhere in that region, where it starts becoming concave up, is the point that's called an inflection point. And you will see how to solve for these in the next video. So now, this brings us to our next idea, which is the second derivative test. And so what that is when f double prime x is continuous at or near some x equals c. So let's say at, then if f prime c is equal to 0 and f double prime c is greater than or less than 0, then f of x has a local maximum or minimum. Sorry, in this case, it's minimum, maximum. A little ahead of myself there. And that's going to be located at critical point, x equals c.